right, we welcome back to a Math 111 lecture. We're going to talk about rational graphs. This is section 4.2 of your text. So we're going to come back to more about this, but let's start talking for just a minute about the sign diagrams. Sign diagrams are going to be useful to us for rational graphs. And pretty much we're going to do them exactly the same way as we did them for polynomials, except that remember with rational functions, there's a denominator that is going to create issues for us because any place that that denominator is 0, we've got values that are excluded from the domain. So we're going to start with those. And instead of putting a 0 above them on the sign diagram, we are going to put a question mark because the function is undefined at those points. So then we're going to proceed as usual. We're going to find the zeros, and we're going to test positive or negative in each of our intervals. Once we've found our sign diagram, there are a few other things we're going to use to help us in sketching our graphs of rational functions. We're going to begin by reducing our function to lowest terms. We're going to find any x and y intercepts. We're going to determine the locations of any vertical asymptotes. And remember, those vertical asymptotes occur where the denominator equals 0, in other words, where the function is undefined. And then we are going to figure out what's going on with the function on either side of those asymptotes. We're going to look at any end behavior, and remember that the end behavior is described by the reduced form of the function after we do long division. We'll talk about that in an example. And then we just sketch our plot. So let's work through this example together. We want to sketch a detailed graph of f of x equals 3x over x squared minus 4. First thing we want to do is put this thing in a form where we can easily see the values that we need to exclude from our domain. That means factoring the denominator. So this will be 3x over x plus 2 times x minus 2. Okay, that means that we've got our number line down here, and we've got tick marks at 2 and negative 2 with question marks above those because those are either holes or they are vertical asymptotes. Now this thing is fully reduced, so we know that they're going to be a vertical asymptote. Okay? And then the other thing we do is we find a 0. So we say to ourselves, if there are any, 3x over x plus 2 times x minus 2 equals 0, where? Well, we know that that happens when x equals 0. So we've got a 0 at 0. So now we pick a value on either side of each of these points, at either side of negative 2, 0, and 2. So if we plug in, for example, negative 3, we find that negative 3 times 3 is negative 9, so that's a negative number, divided by negative 3 plus 2 is negative, negative 3 minus 2 is negative, so I've got a negative divided by a positive, so that's going to be negative. If we test between negative 2 and 0, for example, with negative 1, we'll find that our function is positive. Test between 0 and 2, for example, at 1, and we find that it is negative. And we test above 2, for example, and 3, and find that our function is positive. Now, let's talk about our end behavior. As x gets bigger and bigger and bigger, so we already know that we're positive on above 3. But what happens as x gets bigger, let's say at 10? If you plug it in, you find that the value for y that is 10 is really small. It's down here somewhere. What happens as x gets closer and closer to 2? So if you use your table and your graph, you find that it goes up. So that means that our function looks something like what is sketched here, between above 3. So it gets close to but doesn't cross this vertical asymptote. In the middle, we cross the x-axis. But again, if we look as x gets bigger and bigger and negative, y gets really tiny. So we get really close to this x-axis. So we've got this kind of shape going on in there. Now with graphing calculators, this again gets a little simpler. And whether we take a look at this on Desmos or on our calculator, we will see pretty much the same thing. Here's the kicker though. These graphing utilities, so let me just plug this in. Let me just plug in, and we have to be a little careful on our calculators when we're putting this in. What we've got is 3x divided by, now put your entire denominator in parentheses, x squared minus 4 in parentheses. And if we graph this, let's zoom to a standard window. What you're going to see are gaps, but you're not going to see easily your vertical asymptotes. So you need to know how to find these vertical asymptotes. If we take a look at what Desmos does, y equals 3x divided by x squared minus 4. You see the Desmos also just graphs the function. Now, we know where our vertical asymptotes are. Our vertical asymptotes are x equals 2 and x equals negative 2. Well, let me do that. Okay. X equals 2 and x equals negative 2. Those dotted lines represent our those lines that are going to be dotted in a minute, represent our vertical asymptotes. Yes? The function will never cross the vertical asymptote. Now there's also a horizontal asymptote. This horizontal asymptote is at the x-axis. Functions who have numerators of lower degree than the denominators will always have horizontal asymptotes at the line y equals 0, otherwise known as the x-axis. These functions, horizontal asymptotes, it's important to understand, they describe end behavior, meaning that the functions will approach the horizontal asymptote as x gets bigger and smaller, as in to infinity and away from into negative infinity. But functions can cross the horizontal asymptote in the middle, and that's what we see happening here. All right. So let's do this again. Let's sketch a detailed graph of the function. To x squared minus 3x minus 5 over x squared minus x minus 6. Now we need to factor this thing. The top, let's see. So let's factor the top first. We've got a times c is negative 10, so I think that I can use 2x squared minus 5x plus 2x minus 5. Factor out the x from the first set, yes. And I'll get 2x squared 2x minus 5 plus 2x minus 5. So my function in factored form is going to be x plus 1 times 2x minus 5 over, if we factor the bottom, x minus 3 times x plus 2. So nothing's going to cancel here. So we're going to have a vertical asymptote at -2 and at 3. And we have zeros at -1 and 5/2. Okay, do our sign table. Check a value below -2. We find the function is positive. Between -2 and -1, the function is going to be negative. Between -1 and 5/2, the function is positive. Between 5/2 and 3, the function is negative. And above 3, the function is positive. So we've got positive, and then negative, and then positive, and then negative, and then positive. Okay. We've got our zeros marked. We've got our zeros at -1 and at 5/2. And we've got our y-intercept marked, which we found by plugging in 0. And we would have gotten 5/6, which is almost 1. Now, when I graph these by hand, what I always do is I sketch in my intercepts. So I would sketch in, or not my intercepts, excuse me, my asymptotes. I would sketch in that dotted line and this dotted line. And then I would sketch in my horizontal asymptote. Now, for a function with the same degree numerator and denominator, the horizontal asymptote is given by the ratio of the leading coefficients. So in this case, the horizontal asymptote is here at x equals 2. And then once I knew my positive, negative, positive, negative, positive, I would just sketch in this shape, kind of like that. And whoops, this shape and that shape. So what we're doing is we're actually using our sign table and our zeros to guide our sketching, our sketches. All right. This is mostly practice, and we will do a lot more of this in class. I do want to talk to you about what we call oblique asymptotes. So not all functions are going to have horizontal asymptotes. When we graph this function, we see that it doesn't ever actually level out, which means it does not have a horizontal asymptote. What it has is this slanted line. Let's talk about how we get the equation of this slanted line. So this happens when my numerator has got a higher degree than my denominator. So my numerator is 2x to the third plus 5x squared plus 4x plus 1. And I'm dividing that by x squared plus 3x plus 2. All right, this doesn't easily factor or simplify, so we're going to use long division to figure out what this thing looks like. So x squared plus 3x plus 2 dividing into 2x to the third plus 5x squared plus 4x plus 1. Compare x to 2x to the third. I have to multiply by 2x. We get 2x to the third. I'm going to reverse my signs as I go. 6x squared, 4x. Add, I get negative x squared plus 0 plus 1. I need to multiply by -1. So -1 times x squared is negative x squared, but I'm going to change that sign. So then plus 3x plus 2. Add, and I get a remainder of 3x plus 3. So what that means is that this thing would simplify to 2x minus 1 plus 3x plus 3 over x squared plus 3x plus 2. Now here's the deal. This first part defines the oblique asymptote. So if we look at this slanted line right here, we see that it is a line that crosses the y-intercept at the y-axis. It has a y-intercept of -1 and has a slope of 2. Okay? This line right here, that slanted line, is the line described by y equals 2x minus 1. That is the oblique asymptote. So we've got a vertical asymptote at x equals 2. And let's see, wait. Yes, so y, a vertical asymptote at x equals 2. Well, sorry, at x equals -2. Because if x equals -2, the denominator is 0. There's also a vertical asymptote at x equals -1. Why doesn't it show up as a vertical asymptote? Well, it has to do with the fact that this thing factors. So when I did this division, it turns out that this is 3 times x plus 1 over x plus 1 times x plus 2. So that -1 goes away. In other words, there is no vertical asymptote at -1. There's just a hole in the function. Because -1 is still an undefined point, but when we simplify, that problem is canceled out. It's really how we think about it. So -1 is still excluded from the domain, but it's not a vertical asymptote because we aren't dividing by 0, because it effectively cancels. It's a bit more complicated than that. If you go into calculus, you'll deal with it there. So the important thing for this is that we've got a vertical asymptote at x equals -2, because this guy factors as x plus 2 times x plus 1. But the x plus 1 gets canceled out because it divides away when we do this long division. The whole shebang simplifies as 2x minus 1 plus 3 over x plus 2. Our oblique asymptote, our end behavior, is described by the line y equals 2x minus 1. What this really means is that as x gets bigger and bigger and bigger, the remainder, because we're dividing by x, as x gets bigger and bigger and bigger, this really goes away, and the function is dominated by the 2x minus 1. So at larger values of x, y approaches more closely the value 2x minus 1. This is called an oblique asymptote. Okay, I want you to work through this one and make sure you can sketch the graph of this function and get what we see here from your sketch, at least in approximation, and bring any questions that you have to class or to a web conference. Have a great day and do good math.